this is a continuation of last class. So, in the last class I had started the subject chapter fuels and combustion. So, in the last class I had explained about what is a fuel and what is a combustion, what are the different types of fuels, what are the advantages of fuels, classification of fuels. Let me re-glance once again what do you mean by fuel. Fuel is a chemical substance. After combustion it is going to produce heat and light. Whatever the heat energy produced after complete combustion of fuel will be utilized for various purposes. Majorly it is employed in power generation and also for heating purposes. Okay. So, I will recapture once again. So, in solids there are various types of fuels generally you come across. Some of the examples are wood, peat, lignite, bituminous coal, anthracite coal. These are the various stages of solid fuels. Their calorific value is tabulated like this: 15,826, 15,910, 21,646, 33,494, 34,583. One thing you have to remember here, the calorific value is represented by kilojoules per kg. In case of solids and liquids, it will be expressed in terms of kilojoules per kg. So, in this table, I have given what are the values of calorific value of the solid fuels. This is about the liquid fuels. In this liquid fuels, in the last class you have learnt about how the petrol, kerosene, diesel oil and heavy fuel oil were manufactured. So, these are the some of the natural and artificial fuels. Their calorific value is tabulated like this: 46,692 for petrol, 46,180 kilojoules per kg for kerosene, 45,971 kilojoules per kg for diesel oil, 43,961 kilojoules per kg for heavy fuel oil. So, we will move on to the composition and properties of gaseous fuels. So, these are the different gaseous fuels which are prepared from the natural fuels: coal gas, producer gas, water gas, mount gas, coke oven gas, blast furnace gas. These are the different kinds of gases. Generally we are using it for various purposes. Their calorific value is tabulated like 31,950, 5,025, 11,765, 6,490, 21,420, 3,430. So, this is about the calorific value, and the unit of this calorific value of that particular gaseous fuel will be kilojoules per meter cube. This is about the composition and properties of solid fuels, liquid fuels and gaseous fuels. So, now I am going to elaborate what you mean by calorific value of fuels. So, this calorific value of fuel is also nothing but heating value of the fuel. How we can define it? It is defined as the total quantity of heat which is liberated after the complete combustion of unit quantity of fuel. This is the point you have to underline, this unit quantity. This unit quantity, if it in case of solid and liquid fuel it will be 1 kg, in case of gaseous fuel it will be 1 meter cube. Okay. So, whether it is a solid or liquid fuel, how much heat is going to produce it? The total quantity of the heat which is produced or liberated after the complete combustion of that fuel is called as what? Calorific value or heating value of the fuel. The calorific value of solid and liquid fuels is defined as the quantity of heat liberated by the complete combustion of 1 kg of fuel. Here this has to be underlined, 1 kg of fuel, it is expressed in terms of kilojoules per kg. The calorific value of gaseous fuel is defined as the quantity of heat liberated by the complete combustion of 1 meter cube of fuel at STP condition. In the introduction chapter I had explained about what you mean by STP. STP stands for standard temperature and pressure, and the standard temperature is 15 degrees centigrade, that is we call it as a room temperature, and 760 millimeters of mercury, that is nothing but atmospheric pressure. Whatever the pressure of the air which is available around us is called as atmospheric air. So that value is either 1.013 bar or 760 millimeters of mercury. So the calorific value of gas is expressed in terms of the unit kilojoules per meter cube. This is the unit of the calorific value of gaseous fuel. Here most of the fuel contains hydrogen. During the combustion, hydrogen combines with oxygen to form steam. So steam is nothing but a vaporized form of water. So because the tendency of the hydrogen is to mix with the oxygen, because the air which is used for combustion of fuel contains oxygen. When the hydrogen combines with the oxygen, so it results in formation of the water. That is, since it is in a gaseous state, it is called as steam or water vapor. Calorific value may be expressed after recovering the heat of vapor and flue gases, that is nothing but a product of combustion, that is a heat of product of combustion, or without recovering the heat of product of the combustion. There are two kind of things. Either you have to recover entire heat which is absorbed in the steam as well as flue gases, or else by neglecting that, and you have to count the total heat produced by the complete combustion of the 1 kg of fuel or 1 meter cube of gas. So based on these two parameters, it is classified, the calorific value is classified into two types. They are expressed by two values. One is gross calorific value, that is also called as higher calorific value. It is mentioned as HCV, higher calorific value. Second one is lower calorific value. Lower calorific value is abbreviated as LCV. So let us understand this. So now let us understand what is higher calorific value. Higher calorific value or gross calorific value is defined as the total amount of heat, liberated when 1 kg of solid or liquid fuel or 1 meter cube of gas is burnt. It is completely burnt and the product of the combustion are cooled to the initial temperature at which fuel and air are supplied. Usually the room temperature will be 15 degrees centigrade. I will repeat it once again. Take a 1 kg of fuel or 1 meter cube of gas. You ignite it. Because of the ignition, it undergoes combustion. For the combustion, you require oxygen. So it will draw the oxygen from the surrounding air. So when it undergoes complete combustion, it is going to produce the heat. At the same time, some products of the combustion are left out. So still they carry large quantity of the heat. So in order to recover that heat present in the product of the combustion, you have to allow it to cool till the temperature becomes 15 degrees centigrade. The total amount of the heat starting from the initial combustion to till the product of the combustion is brought to the temperature of 15 degrees centigrade is called as higher calorific value, or it is also called as gross calorific value. This will help us to rate the fuel, and also it will be helpful for selecting the kind of fuel which is required for different applications, because higher calorific value will help us. So what is the quantity of the heat will be liberated from the particular type of the fuel which we are using it for different applications. Then lower calorific value. Lower calorific value is also called as net calorific value. It is defined as the total amount of heat liberated by complete combustion of 1 kg of fuel in case of solid and liquid, or 1 meter cube of gas without the condensation of the steam formed. Here we are neglecting the product of the combustions. Here we are not considering it. It is given by the difference between higher calorific value and the latent heat absorbed by the water vapor. I wanted to explain about what you mean by latent heat. Latent heat is the heat required by the water for vaporizing from liquid state to vapor state at the saturation temperature, that we call it as a latent heat. This is nothing but a amount of heat required or absorbed by the water to get evaporation. That means that, so when you draw the atmospheric air for the combustion of fuel, it contains moisture. That moisture, what it does? It absorbs some quantity of the heat. The moisture is nothing but a suspension of water particles in the air. It absorbs the heat and escapes to the atmosphere without doing any work. There is a huge loss of heat in the moisture. It will escape in the form of steam. So, when the escaping steam is not considered, so that means that the amount of the heat lost to the water vapor, if you subtract it from the higher calorific value, it results in giving the lower calorific value or net calorific value. This will give you in actual practice what is the net heat available at the reaching point. This is what we call it as a lower calorific value or net calorific value of fuel. So, we are expressing it in terms of equation. Lower calorific value is equal to higher calorific value minus ms into L, kilojoules per kg in case of solid and liquid fuel, where ms stands for mass of water vapor formed per kg of fuel burnt, that is approximately equal to 9 times the hydrogen, that is H2 stands for percentage of hydrogen by mass, not by volume. It will be expressed in terms of by mass. L stands for latent heat of water vapor corresponding to room temperature, that is 15 degrees centigrade. The amount of heat required or will be utilized by the water to convert into steam. What is the amount of heat required to convert 1 kg of water into steam? That is equal to 2466 kilojoules per kg. Then the value of latent heat will be depend upon the temperature at which we are heating the water. It varies from one temperature to another temperature or one pressure to another pressure. This will not be same. As the pressure increases, latent heat decreases. As the pressure decreases, latent heat increases. Okay. Therefore, the lower calorific value can be obtained directly by subtracting amount of the heat lost to the water by higher calorific value, gives you net calorific value or lower calorific value. Thus the equation can be written as like this: LCV is equal to, LCV stands for lower calorific value is equal to higher calorific value minus ms into L. The value of L is 2466 kilojoules per kg, or ms is nothing but 9 H2. H2 is the mass of the hydrogen. So, this is the appropriate equation, we are using it to find out lower calorific value. Next, analysis of fuel. The quality of fuel depends on its composition. Here, what is the percentage of carbon, what is the percentage of hydrogen, what is the percentage of sulphur, nitrogen, hydrogen. They are all the composition of the particular given fuel. How do you analyze that particular fuel? What is the percentage of carbon, hydrogen, sulphur, nitrogen, so present in that particular fuel? So, there are two methods we employ it to know the composition of fuel. Those two methods are, one is ultimate analysis, another one is proximate analysis. One is ultimate analysis, another one is proximate analysis. What is ultimate analysis? Ultimate analysis gives the percentage content of mass of carbon. In this we are considering only mass, you have to remember here. It is going to, ultimate analysis is going to give you mass of carbon, mass of hydrogen, mass of nitrogen, mass of oxygen, mass of sulphur and mass of ash content present in 1 kg of solid or liquid fuel. Their sum is taken as 100%. That means that mass of carbon, mass of hydrogen, mass of nitrogen, mass of oxygen, mass of sulphur and mass of ash in 1 kg is taken as 100%. Moisture and volatile matter are expressed as a separate items. They are not considered in the main things. Okay. They are separate, they are completely separated out of the percentage of the mass of the particular composition of the fuel. The analysis helps to calculate what is the minimum amount of air required for complete combustion of 1 kg of fuel and also to determine the calorific value of fuel. If this analysis would not have been there, then it would have been very difficult to analyze the particular given fuel, because we will not be knowing, we will not be sure what is the total amount of the heat it is going to produce. For the determination of the calorific value, this analysis is very important. Not only that, because for the combustion of fuel it draws the air. For the combustion of fuel it is going to draw the air. So, now what is the minimum air required for combustion purpose? That will be analyzed with the help of this analysis, and this analysis is called as what? Ultimate analysis. Next, proximate analysis. Proximate analysis is very simple and it gives the percentage content of by mass of fixed carbon. Carbon not combined with any other elements of fuel. That means that we are considering only the percentage of fixed carbon by mass. Volatile matter, that is combination of carbon, hydrogen and other gases which distill easily. Moisture and ash in solid or liquid fuel. The sum of these quantities are taken as 100%. In previous case, we had neglected the moisture and volatile matters, where in case of this it is considered in this. Okay. In this proximate analysis, sulphur is determined separately. Proximate analysis will also be used for finding the calorific value of fuel and to calculate the theoretical air required for complete combustion of 1 kg of fuel. Whatever the air required, theoretically this analysis will help you to determine the total quantity of the air required for the complete combustion of the fuel can be analyzed through this analysis, and this analysis is called as what? Proximate analysis. In this, mass of fixed carbon is taken separately and combination of carbon, hydrogen and other gases also taken separately. Okay. Fixed carbon separately, volatile and combination of carbon with hydrogen is taken separately, as well as moisture and ash in solid or liquid fuel is taken separately. Okay. So, combining of all this put together is taken as 100% in the case of proximate analysis. Next, determination of calorific value of fuel. The calorific value of fuel depends on its chemical composition. You have to remember one thing here, whatever the calorific value or heating value will be given by the fuel will be depend upon its chemical composition. So, chemical composition will decides what is the amount of the heat it is going to liberate after complete combustion. Gross calorific value is the sum of heat liberated by complete combustion of each constituents of 1 kg of fuel. Dulong proposed a formula for calculation of calorific value of solid and liquid fuel from their constituents. The Dulong formula for calculating HCV is given as below. Higher calorific value is equal to 33,800 into mass analysis of C, 1,44,000 into H2 minus O2 by 8 plus 9270 into S gives you kilojoules per kg. This is the Dulong formula for calculating the higher calorific value. So, now this is that formula is used to determine the calorific value of fuel, because it is required to know what is the complete sum of the heat liberated by complete combustion of each constituents of particular fuel, where C, H2, O2 and S represent the mass of carbon, mass of hydrogen, mass of oxygen and mass of sulphur respectively present in 1 kg of fuel, The term H2 minus O2 by 8 represent net hydrogen contribute for calorific value. So, whatever the contribution given by the H2 minus O2 by 8 gives you the net contribution to that. O2 by 8 is the amount of hydrogen combines with oxygen to form H2O. So, this oxygen is mixing with the hydrogen to produce the water. 1 kg of hydrogen combined with 8 kg of oxygen, the numerical value is 33800, 14400 and 9270 represent heat evolved due to the combustion of unit quantity of carbon, unit quantity of hydrogen and unit quantity of sulphur, and they are expressed in terms of kilojoules per kg. So, these numerical values have got very significant, they are very significant. So, they are the one which is going to represent what is the heat evolved by that particular chemical, whether it is in the case of carbon or in the case of hydrogen or in the case of sulphur. To determine the calorific value of fuel, we are using the various devices. Okay. So, now there are two devices we are using it. One is the bomb calorimeter, another one is Junkers gas calorimeter. To find out the calorific value of solid and liquid fuels, we are using the bomb calorimeter, where in case of to determine the calorific value of gaseous fuel, we are using Junkers gas calorimeter. So, now let us understand what is the bomb calorimeter, how it is constructed and what is the procedure we adopt to calculate the calorific value of the fuel using this device. So, now this device will help us to determine the calorific value experimentally, because experimental setup is very much required to determine what is the calorific value of the particular given fuel. So, this bomb calorimeter will be very useful to find higher calorific value of solid and liquid fuels. So, this device is mainly employed to find out the calorific value of solid and liquid fuels. So, now this is a sketch. So, it consists of these main parts. Okay. So, first one is it consists of bomb, stirrer, chamber, intake valve, release valve, oxygen supply valve, ignition bulb and crucible, and thermometer to record the temperature of this. So, I will describe the bomb calorimeter. The figure which I just shown, it is going to illustrate the bomb calorimeter. First thing you have to remember, bomb has to be very strong. So, because whatever the fuel we are going to burn, it has to withstand the pressure of that. So, that is what it is made up of, stainless steel. It is provided with 2 valves at the top. One is to supply the oxygen. So, for that we are using oxygen supply valve, and the other is product release valve. So, we have to release the gases which is produced during the combustion of the fuel. The entire bomb is immersed in a bath of water contained in a copper calorimeter, and the water is kept at the uniform temperature by stirring it. The bomb contains a platinum crucible to hold the fuel and the coil to ignite the fuel electrically. The calorimeter is surrounded by outer vessel which form the air space around the calorimeter. So, this is going to minimize the heat losses to the surroundings. So, now we have to understand what is the procedure we are following it to analyze the calorific value experimentally. You have to take 1 gram of coal in the form of pellet is placed in the crucible. First you take the crucible, in that you have to place 1 gram of coal. The coil is connected to the external circuit to the battery through the electrodes. There will be 2 electrodes, so they are connected to the battery. From that electricity is conducted into the fuel. So, for the combustion of fuel you require oxygen. The oxygen is supplied to the bomb to a pressure up to 25 to 30 atmosphere. You see here the pressure of the air at which it is supplied into the bomb. After charging, the valves at the top of the bomb are carefully sealed. After supplying the air into the chamber, it need to be completely sealed. The bomb is placed in a known mass of water which is contained in a calorimeter. The bomb, which is a device which contains the fuel in a crucible, entire thing has to be placed inside the water, and it has to be, the mass of the water should be known to us. Then after placing the bomb, you have to note down the initial temperature of the water which is need to be measured, and when the thermometer shows a steady temperature, the coal sample is ignited by closing the electric circuit. You have to supply the current to the crucible through the electrodes. It is ignited and stirrer is continuously operated, because when the fuel undergoes combustion, it liberates the heat. That heat is transferred to the surrounding water continuously, and in order to get the uniform temperature around the bomb, you need to use the stirrer. The stirrer, when it is operated, it stirs the water, and because of stirring, so uniform temperature is obtained around the entire bomb. The temperature readings are recorded at the interval of half minute until the maximum temperature is attained. Then the bomb is removed from the calorimeter, and the pressure release valve is opened to reduce the pressure in the bomb to atmospheric. The bomb is then opened and the crucible is inspected to ensure complete combustion. From the known value of water equivalent of the calorimeter, the calorific value of the fuel may be obtained from the test result. Now, you see here, I will show you. The center portion is a bomb. It consists of 2 valves. One is oxygen supply valve, another one is release valve, and there is a crucible, and the crucible is connected to the 2 electrodes through the fuse wire. So, now that the crucible, the fuel has to be placed in a crucible, and it is connected to the electrical fuse wire. Then after that, you have to charge this bomb through the oxygen supply valve up to 25 to 30 bar. After doing this, entire thing is placed in a calorimeter, so known quantity of the water. So, there is a thermometer. So, through the thermometer you have to record the initial temperature of the water. Then from the battery you have to switch on the battery. The electricity is conducted through the fuse wire and it gets ignited. The fuel undergoes complete combustion. As a result of combustion, the heat is liberated out of the crucible, out of the fuel, and that fuel, the product of the combustion, so that is carries the heat, it will transfer the heat to the water. There is a stirrer that is going to mix water uniformly, so that so temperature has to be recorded every half minute till it gets the maximum, it records the maximum temperature. So, after that you have to stop this experiment, remove the bomb from the calorimeter, you have to release the gases which are left present in the bomb till it is brought back to the atmosphere. Okay. You know the mass of the water, you know the mass of the fuel, you know the rise in temperature of the water. Then we have to conduct the calculation. You have to make the calculation after conducting this experiment. Let M be the mass of the fuel burnt. Capital M is the mass of the water present in the calorimeter. ME stands for water equivalent of calorimeter, because whatever the heat absorbed by the calorimeter is expressed in terms of water equivalent. T1 is the initial temperature of the water before ignition, T2 is the final temperature of the water after combustion. So, C is the specific heat of the water. It is generally taken as 4.187, but in calculation it is taken as 4.2 kilojoules per kg Kelvin. This is the standard specific heat of water. Next, heat liberated by fuel given by the equation m into HCV, m into higher calorific value. Next, heat absorbed by water and calorimeter is given by the equation. Capital M is the mass of water present in the calorimeter. Me is the water equivalent of calorimeter, because not only water absorbs the heat, the calorimeter also absorbs the heat. The heat absorbed by the calorimeter is expressed in terms of water equivalent into calorific value of water into rise in temperature. T1 is the initial temperature of the water and T2 is the final temperature of the water, and neglect the losses. So, now you have to equate the equation. Heat liberated by fuel in the heat liberated by the fuel is equal to heat absorbed by water and calorimeter. You have to equate the equation. M into HCV is equal to m plus me into C into T2 minus T1. Therefore, higher calorific value is equal to m plus me into C into T2 minus T1 divided by m. This is the equation we are using it to find out higher calorific value of the given fuel. Suppose if you consider the mass of fuse wire, and calorific value of fuse wire, the equation can be modified as m into higher calorific value of fuel. M stands for mass of fuel, and fuse wire also used, right. So, MW stands for mass of fuse wire and its calorific value is equal to m plus me into C into T2 minus T1 plus Te. So, this is the equation we are using it to determine the gross calorific value or higher calorific value of the fuel. Okay. So, in examination you have to draw the sketch very neatly, and after drawing the sketch you have to describe that bomb calorimeter. So, what are the parts it contain and what are the sole purpose of each and every parts, and also you have to write down the procedure we are using it to determine the calorific value. Then you have to write down the final equation of finding out higher calorific value. This is the experimental setup which is used to find out the calorific value of solid and liquid fuels. Next, we are moving on to the Jenka's gas calorimeter. The name itself tells you that this calorimeter is used to find out the calorific value of the particular given gas. You can see here in the sketch there is a gas meter. That gas meter is used to record the volume of the gas supplied to the gas burner, and there is a pressure regulator. The purpose of the pressure regulator is to regulate the pressure of the gas, because usually when you supply the gas to the burner, the pressure may not be uniform. So, because when the pressure is not uniform, there will not be proper combustion of fuel. So, there will be a flickering of the flame. That can be avoided by fitting the setup with the pressure regulator. There will be water tubes and gas tubes. So, there are separate tubes which are provided for the movement of the gas as well as movement of the water, and there are two places, one is inlet water inlet, another one is water exit. Similarly, the gas exit and also the burner combustion chamber, and there is a two thermometers, one is inlet water temperature, another one is outlet water temperature. This is the complete setup of the Jenka's gas calorimeter. The Jenka's gas calorimeter is used to find the higher calorific value of gaseous fuel. It is a steady flow type gas calorimeter. It consists of inner combustion chamber in which the product of combustion moves upwards. This chamber is surrounded by water jacket through which number of tubes pass. Heat liberated by the combustion of gas is absorbed by water. Thermometers are provided on the calorimeter to measure the exact gas temperature. This arrangement is made to ensure the complete transfer of heat of combustion to water, and the temperature of exit gases is nearly equal to the room temperature. So, one thing you have to remember here, the Junker gas calorimeter is used to find the higher calorific value of gaseous fuel. It is a very steady flow type. It consists of inner chamber which is meant to carry the product of the combustion. So, this chamber is completely surrounded by water jackets through which a number of tubes passes around. Heat liberated by the combustion of gas is absorbed by the water. The main intention of the flow of the gases is made here to transfer the heat to the surrounding water. Thermometers are provided on the calorimeter to measure the exit gas temperature. This arrangement is made to ensure the complete transfer of heat of combustion to water. Procedure: a measured quantity of the gas whose calorific value is to be determined is supplied to the combustion chamber through the gas meter. The sole purpose of the gas meter is to measure the volume of the gas supplied to the gas burner, and the pressure regulator which records the pressure of the gas by means of a manometer. We are using a device called as pressure regulator. It is going to regulate the pressure of the gas. That means that whatever the gas supplied to the burner, it is supplied at constant pressure. The water enters the calorimeter under constant head at the same pressure, because there should not be any variation of the pressure. The pressure of the water has to be maintained constant. The temperature of the water entering and leaving the calorimeter are noted by thermometers. The gas is mixed with sufficient air and burns in a burner. So, for the combustion of fuel you require a air. That air, sufficient air has to be drawn to the system, and there we have to see to that there is a complete combustion of the gas. The hot product of combustion move upward in the combustion chamber and then moves downward through the flues and finally escapes to the exhausted to the atmosphere. The temperature at exit is recorded by a thermometer and nearly is equal to the room temperature. That means that product of the combustion is cooled to the room temperature. The water moves in a direction opposite to that of hot gases in flues. When the gases moves from one direction, the water moves in the other direction and goes out from the upper portion. Its temperature and quantity of is recorded. There is a provision for recording the quantity of the particular fluid and also to measure the particular temperature of the particular fluid. Water formed by the condensation of steam is also collected and measured in the system. Since the process is one of steady flow at low velocities, the heat lost by the product of the combustion, that is heat liberated by complete combustion of gas, is equal to the heat gained by water. So, in order to understand what is the calorific value, so this point has to be understood. Whatever the heat liberated by the gas is equal to the whatever the heat gained by the water, and most of the steam is exhausted in the exhaust gas is condensed back. The gas calorimeter therefore measures the higher calorific value of gas. The lower calorific value can be calculated from the measured quantity of steam condensed in the calorimeter. That means that after calculating the higher calorific value, you have to subtract that value with the amount of heat lost to the steam. So, when you subtract these two, you will get lower calorific value. I will explain this once again with this sketch. In the sketch you can make it out. There is a gas meter is connected to the gas supply. So, there is a thermometer which is used to record the temperature at which the gas is supplied. This gas from the gas meter is going to record the volume of the gas supplied is going to be get supplied to the burner. From the gas meter, the gas goes to the pressure regulator. The pressure of the gas is recorded in the pressure regulator. Then it is supplied to the burner, and air is also supplied from the atmosphere for the combustion. There are two types of flue tubes. One is water tube, another is gas tube, flue tube. In a flue tube, hot gases are flowing. In a water tube, there is a water passes. Both water and gas move in the opposite direction. There is a water inlet. From the water inlet, water goes inside to the gas calorimeter, and there is a point where we need to record the inlet water temperature. After flowing through the tubes, this water absorbs the heat from the surrounding gases. The gas transfers the heat to the water. As a result of that, water temperature rises. So, water absorbs the heat. As a result of absorbing the heat, the temperature of the water increases. That temperature you have to record it with the help of the outlet water thermometer. Okay. So, now the product of the combustion which are resulting out of the combustion will find the way to exhaust to the atmosphere. It need to be cooled. Okay. So, this is the experimental setup, and this is the procedure we have to use it to conduct this experiment, and this experiment will help you to analyze the calorific value of the fuel, experimentally. So, now we have to equate heat liberated by the gas is equal to heat absorbed by water. Volume of the gas into higher calorific value is equal to mass of the water into specific heat into T2 minus T1. Higher calorific value is equal to mass of the water into specific heat into rise in temperature divided by volume of the gas supplied to the burner. V naught is the volume of the gas at STP. It is expressed in terms of meter cube. Capital M is the mass of the water collected in kg. C is the specific heat of water. It is expressed in terms of 4.2 kilojoules per kg Kelvin. T2 is the final temperature of water, and T1 is the initial temperature of water, which is expressed in terms of degrees centigrade. So, this is the equation we are using it to determine higher calorific value of gas. And if the product of the combustion is cooled to the room temperature and the steam formed is condensed, and if you note down the heat absorbed by that steam, if you subtract with the HCV, you are going to get the lower calorific value of the fuel. So, this is a problem we can understand. So, what is the how to calculate the calorific value of fuel? I will read out to the problem. Find the higher calorific value of the fuel whose composition by mass is given as follows. Carbon is given 90%, hydrogen is given 3%, sulphur is given 0.8%, and the remainder being ash. So, now you have to note down the data first. Composition of 1 kg of fuel, carbon C 90% or 91%, that is 0.91 kg, hydrogen 3%, that is 0.03 kg, sulphur 8% divided by 100 gives you 0.08 kg. From Dulong's formula, you have to this equation. So, Dulong formula gives you like this: HCV is equal to 33800C plus 144,000 into H2 minus O2 by 8 plus 9270S kilojoules per kg. So, hydrogen minus oxygen combined together he has given 0.03 kg. You can see here hydrogen is given 0.03, oxygen he has not given in this. So, when the oxygen value is not given, it will be taken as 0. When it is taken it as 0, the value of S2 minus O2 by 8 will be 0.03 kg. So, substitute values in this. The value of carbon is 0.9, value of hydrogen is 0.03 and value of sulphur is 0.008, and substitute in this equation. 33800 into 0.91 plus 144300 into 0.03 plus 9270 into 0.008. When you substitute in this equation and if you do the calculation, you will get 35152 kilojoules per kg. Okay. This is the total calorific value of the given fuel which is going to give after complete combustion. This value is called as higher calorific value of the given fuel. When the fuel consists of carbon, hydrogen and sulphur in the percentage of 90%, 3% and 0.8%. So, Dulong formula can be used to find out total calorific value of the fuel, that is nothing but higher calorific value of the fuel. Second problem, a sample of coal has the following composition. A sample of coal has the following composition by mass: carbon 75%, hydrogen 5%, oxygen 8%, nitrogen 4%, sulphur 2%, ash 6%. Calculate higher calorific value and lower calorific value. So, he has given a sample of coal. Here he has mentioned the composition of the different constituents present